We are on FRQ topic number 9. This is series, convergence, and divergence tests. And this first page in your packet is all important. This is a little recap of all of our convergence and divergence tests. Okay, so I started to highlight things on a different one and I found myself highlighting everything. So just know that it's all important. On FRQs, these are the tests I've seen most frequently on FRQs. Okay? Remember that a series converging means that the sum is one real number. That's what it means for a series to converge. The sum is one real number. Diverging means it is not one real number. It's convenient to think of it as infinity or negative infinity, but that's not necessarily the case. It just might not be able to be determined. Diverging means the sum cannot be found. Okay, so we have these convergence and divergence tests. We started out with the nth term test. That is if it's top heavy. The limit of the term of the a sub n term is not 0. If that is the case, then we diverge by nth term test. If it's not top heavy, that's when you go to one of your other tests. The geometric series test. Remembering that if it converges to this value. The first term divided by 1 minus r. So if if the absolute value of r is less than 1, it converges. Greater than or equal to 1, there should be an equal to sign under there, it diverges. Okay? Alrighty. The alternating series test. If the terms are alternating in sign and decreasing in magnitude to 0. It's not the series that is alternating in sign and decreasing in magnitude to 0, it is the terms. They are alternating in sign and decreasing in magnitude to 0. Then the series converges by alternating series test, AST. Okay, so if this is alternating and bottom heavy, then it converges. Now, it can converge absolutely or conditionally. If it would converge even if it was not alternating, then that's absolute convergence. If it converges only because it is alternating, then it converges conditionally. You cannot diverge by alternating series test. If a series diverges after you've applied the alternating series test, then it diverges by nth term test because it must be top heavy. Okay, p-series test converges if I think of it as if the bottom is big. So what would make the bottom big? The bottom would be big if p was greater than 1. Diverges if p is less than 1. Okay? Harmonic series is when p is equal to 1, so this is the harmonic series, and it diverges. We had two comparison tests, the limit comparison test and the direct comparison test. In FRQs, I almost exclusively would use the limit comparison test. Set up the limit. We want the limit to be a finite positive number. Okay? All right. The integral test is I've seen this in several FRQs. If the function is positive, continuous, and decreasing, okay, then the series does whatever the function does in this, or whatever the integral does. Okay, so they either both converge or both diverge, is as long as the function is positive, continuous, and decreasing. Those are the magic words. Okay, alrighty, the ratio test. We've done this quite a bit. Okay, set up the ratio test, the n plus 1 term over the nth term in a limit. If that is less than 1, it converges. Greater than 1, diverges. Equal to 1, can't use it. We have to use a different test if that limit is equal to 1. Do not use this if you have only polynomials, okay? Because that's when you'll get an equal to 1. Alrighty, I went on. I have some more notes to recap things from this unit. This was a little one-pager as a chart. It's all of the tests and requirements as a chart. It's what I just went over, but in a chart format. And then let's talk a little bit about error bounds. What's the difference between alternating series error bounds and Lagrange error bounds? Alternating series error bounds can only be used if the terms are alternating in sign and decreasing in magnitude to 0. Okay? Lagrange error bounds can be used for everything else. Okay? All right. So, in general, we're approximating a series. So in this series starts with when n is 3. So the first 5 terms, the sum of the first 5 terms would be from a sub 3 to a sub 7. The error is everything else. The error bound involves only the first term. Okay, the error bound involves only the first missing term. Okay, so error is everything. Error bound, think it is something having to do with the first term of the error. Okay. Alrighty. So in an alternating series error bound, as long as the terms are alternating in sign, decreasing in magnitude to 0, the error bound is the absolute value of the first unused term. Lagrange, it still involves that first unused term. It still does, except it is written as in the form of a Taylor series term. Derivative x minus c to a power over factorial. All the form of a Taylor series term. Okay, that's Lagrange. Okay, remember all numbers, no letters. Alrighty. Use Lagrange error when you're told to use Lagrange error. For alternating series error, you may not be told to use alternating series error. You may have to know to use it. Okay? You will be told how many terms there are. The error is the magnitude of the next term. For Lagrange, you're told what degree to use. Error is always the next degreed term. Okay? Alright, so if they tell you degree 6, you use degree 7. Okay? Alright. Okay, let's do a problem. I pulled out number 14 from your packet. I put in your packet several multiple choice questions just to review with you multiple choice format on these. And then I put in a few FRQs. Okay. They give us a sub n. Okay, so state the conditions for the use of the integral test, then use the integral test to determine whether the series converges or diverges. Okay, so first of all, we want the conditions for the integral test. Well, I know it's when the function is positive, continuous, and decreasing. But if I write the function, what in the world would that mean? There is no function in play here, right? So I have to first name the function. I'm going to name the function. So I'm going to say f of x is equal to 1 over x squared plus 8x plus 20. And then I'm going to say is positive, continuous, and decreasing. for x greater than or equal to 2. Okay? Alrighty, so we need to remember that. I remember one time I had a class who, there was a student in this class named Peter, and my kids, to remember positive, continuous, and decreasing, they would always say, Peter can't drive. Peter can't drive. Peter can't drive. And I thought it was adorable, even though I'm sure he was a fantastic driver. But that's how they remembered that. So somehow think of some way to remember positive, continuous, and decreasing. Alrighty, so now we are going to use the integral test. So I need to set up the integral test. I'm using the same boundaries on my integral that are on my series. And then I have my function. And now I want to evaluate that function because I want to know if that diverges or converges. So now this becomes an integral problem, and I notice at the bottom I can use completing the square on that denominator. So I'm going to complete the square on the denominator. Keep your x squared plus 8x. Half of 8 squared. Half of 8 squared is 16. But I have 20, so I add 4 more down here. Okay. Now factor this part. X plus 4 squared plus 4 over 1. Now I'm ready to integrate this. So this is going to be an arctan, right? And oops, I changed that infinity to an 8. Let's go back to infinity. Top boundary is infinity, so I write this as a limit. Limit as the top boundary b is going to infinity of, okay, it's arctan u over a, right? U over a. U is the square root of this, a is the square root of that. So u over a and then arctan gets the 1 over a out in front, and we are evaluating that from 2 to b. Okay, first thing we do is put b in for x, and let b go to infinity. Arctan of infinity. Okay, arctan of something going to infinity, that's our pi over 2. So I have 1/2 times pi over 2 minus 1/2 times, now we're going to put 2 in for x. 2 in for x, that would be arctan of 6 over 2 is 3. And that would be a safe stop spot. This is not infinity. This is just a number. So the integral converged. The integral converged. The integral 2 to infinity of f of x converges. So the series converges. So at the end, make a statement. Don't get lazy. Just make your statement. Remember that you are communicating here. So make your statement well. Okay, part B. Determine whether this series converges or diverges. State the conditions of the test used and show the work for determining convergence or divergence. Okay, so the first thing I'm going to do is write out what this expression is. What would be this expression? So n times a sub n. What is n times this? Well, would you agree? I would put the n, I would multiply the n to the top, right? So we are finding our series is this. So often, you guys, I see students who they will write this and they'll write n times this, and they won't know what to do with it. Use your head, you guys. Use algebra. Okay, when you're multiplying a fraction times n, you multiply it. All right. So I see that this is going to behave like 1 over n. Therefore, I'm going to compare with the diverging harmonic series 1 over n. Make sure you write it as a series. Okay? And say what it is doing. Now I'm going to use the limit comparison test. So the limit comparison test has a limit. What I am given divided by what I'm comparing it to. So dividing by 1 over n is the same as multiplying by n over 1. So this is n squared, and there's an n squared on the bottom. N is going to infinity, so these two are negligible. This behaves like n squared over n squared, which is 1. That is finite and positive. Therefore, this series does whatever this series does. So that series diverges by limit comparison test. Okay? Alright, you don't have to show this step right here. You could have skipped right to this step, but you do need to say what that limit is. Alright. Did not state the conditions of a test. What are the conditions of a test? So before I went on to part C, you guys, I looked back to make sure I had done everything, and I noticed I never did state the conditions. This was one of the conditions, okay? But also for the any comparison test, we have to make the statement that both of the series terms are greater than or equal to 0 for n greater than or equal to 2. Okay? Alright, part C. Now we're determining whether this series converges absolutely, conditionally, or diverges. So we just showed that this one diverged, right? We want to know, we're going to make it alternate now, right? Now what if it's alternating? Then would it converge? Okay? It's definitely not going to converge absolutely though, because we just showed that this diverges. So it's either conditional convergence or it's still going to diverge. So first we're going to write it out. So we'll have -1 to the n times n on top, n squared plus 8n plus 20. Okay, this is bottom heavy, right? And it's alternating. So I'm going to say that. Okay, the terms are alternating in sign and decreasing in magnitude to 0. So the series converges by AST. Okay? Alternating in sign, decreasing in magnitude to 0. Alrighty, but we already showed that the non-alternating version diverges, as shown in part B. So that series converges conditionally. Alrighty? Part D. So now we're going to let S be this sum, that's the alternating series that we just had. Let S sub 9 be the sum of the first 9 terms of the series. Show that the error in the approximation is at most 0.05. Okay, so the alternating series, we already said it's alternating in sign, decreasing in magnitude to 0. We use the first 9 terms to find the partial sum, and we want to know something about the error. The error is the absolute value of the first unused term. The first unused term. So first of all, if we use 9 terms of this series, that would be not when n is 9, right? Because we're starting at 2. 2, 3, n is 2 would be the first term, n is 3 would be the second term, n is 4 would be the third term, n is 5 would be the fourth term, 6, 7, 8, 9, n is 10 would be the ninth term. So we want when n is 11. So if you need to write that out, write it out, okay? But we want when n is 11. n equals 11 will be the 10th term. So I'm going to put 11 in for n. So we'll have negative, in fact, I don't need to put, I was about to put -1 to the 11. It doesn't matter. Because we're taking the absolute value, I can leave out the -1 to the 11 and just go straight to the rest of it. That's the error bound. That's the error bound. It's the first unused term. That's the error bound. And that is at most, so less than or equal to 0.05. That's all you need to show on that one. Okay, best thing to do is to review these. So I gave you plenty of review problems there.